Hello? All right, here we go. We're constructing a confidence interval for the mean of all the light bulbs. We know that we have a sample of 31 light bulbs. The mean lifetime is 531. Standard deviation is sigma equals 33. So first thing you want to do is draw a picture. When you draw a picture, this area on the inside is 0.95. Area on the outside is 0.025. When you look up 0.025 on the chart, you get 1.96. This is negative 1.96. Do we agree? We agree. Part B, you're going to have to write down the formula. The formula is x bar minus e is less than mu, which is less than x bar plus e, where e is equal to z times sigma over the square root of n. Part C is 531 minus 1.96 times 33 over the square root of 31. Do we agree? Is less than mu, which is less than that whole thing plus whatever. You got the idea. 531 minus 1.96 times 33 divided by the square root of 31. Square root of 31 is 5 and some change. 1.96 divided by 5 and some change is going to be about 0.36, and it's going to be about 0.4, so 1.32. No, 13.2. It's a little less than that. So about 517 or so. What'd you get? 519.38. Perfect. Less than mu, which is less than 542.62. Now, I'll remind you that you only need to go one decimal place. You're only required to go one decimal place further than the data set was started with. This is to the nearest whole number. So typically you would make this 519.4 and 542.6. Part D, how do we interpret? Go ahead, Liam.
If we continue to take the samples of size 31, we expect 95% of the sample mean to be between 519.38 and 5.9.
If we continue to take samples of size 31, we expect 95% of the sample means to be between 519.38 and 542.62. Okay. E, what is it? Since n is greater than 30, the sample mean is distributed. Okay. Going once, going twice, sold. Additionally, if you want to check this on the calculator, let me show you how to do it. You're going to go to Stat, Test. You're going to go down to option number 7 where it says Z interval. You're going to have stats there, so you're going to do sigma is 33. X bar was 518. Is that right? 531. N was 31. And we're doing a 95% confidence interval, yes? What did we say it was? 519.38, 542.62. Okay. Now, some of you yesterday had a question that wasn't really a question, it was more of a statement, which was, okay, well, when I do it, the answer I'm getting is not the same answer the calculator is getting. There seems to be a little bit of a difference. First of all, the calculator is not looking the value up on the damn chart. Okay, it's calculating it. So if you use a value like 2.33 because that's the one closest to it, well then the calculator is not using 2.33. The calculator is using 2.3654195667, whatever it is, right? It's using an actual absolute answer. The other thing is, like in the case of p hat, where you take 18 divided by 57 and you round that off to be 0.26, the calculator may not round that off. It may say the answer is 0.259464442, and it uses the whole thing. So there ought to be, with some problems, you ought to expect a little bit of variation there. Now, there's no variation here because 1.96 is the exact z value you need. X bar and sigma we typed in and we told what it was. So that's why you get the exact same thing. Okay? But it's not always the case. I just wanted to point that out. Okay. It is confusing, though, when you're checking your answer on the calculator, your answer is not the same as the calculator. What you got on the test, you're like, shit. One of us is wrong. And I'm pretty sure it's not the calculator. Okay? All right. Any questions on that? All right. So we're going to now move our discussion, and we need to look at a problem like this. And typically we wouldn't look at a problem like this, but Krista wants to do it, so I guess we probably ought to go ahead and do it. Yeah, I know you want to work on a problem like this. This is like your purpose in life. So we want to try to find a confidence interval for the standard deviation, not standard deviation. For the mean. I'm just going to delete standard deviation and write mean. Bam. I can do that. I got the marker. Okay. Now, how do I find a confidence interval for the mean if I don't know the mean and the standard deviation? Like before, it just told me, like, yo, Rocky style. Yo, here's the mean. Okay? So for this one, you have to find the mean and the standard deviation too, right? You have to find both of them. So now how do you go about finding the mean and the standard deviation? Okay, so to find the mean, you add them all together, you divide by the standard deviation, or the total, right? How do you find standard deviation? You just pray on it, don't you? Dear Lord, let my hand be your hand. Guide me to the standard deviation. $3,552, Lord's will. Now, how do you go about doing it? Seriously. N times P times Q is for a binomial. That's actually a pretty good idea, but it's for a binomial. You just put it in the calculator. You were going to say that. You didn't want to sound dumb. You would have sounded really smart. I won't tell you what you sound like when you say I was going to say it, but I didn't want to sound dumb. I won't tell you how that sounds. Oh, jeez. All right, let's go ahead and type all this into the calculator. We're going to go to Stat, Edit. Everybody remember this? How do I get rid of the values in L1? Up and hit Clear. Enter. All right, now we're going to type them all in, right? So 65, 49, 55, 95, 87, 67, 40, 72. 1, 2, 3, 4, 5, 6, 7, 8. We got 8 values. Everybody see that? How do you find the mean and standard deviation? Stat, calc, one variable statistics. pressed the wrong button. So now what we have is the mean and the standard deviation, yes? Well, with this information, can I solve it? Well, I can, except for one thing. Notice that sigma is not known. And I say that because over here, I've made that point to say, hey, sigma is known. It's not S, it's sigma. Remember that? And I said that clears it right up for some of you, and you're going like this. No, it don't, because I didn't care anyway. Over here, it doesn't tell me what sigma is. Now, some of you will look at me and go like this. Well, it does tell me. Right there. Sigma. Found it. No. We don't deal with that. Okay? If the problem doesn't state what sigma is, you don't know what sigma is. This is a sample. It is not a population. Okay? So, in this case, because we don't know sigma, we only have 8 values. A t-score. We're going to have to go to a t-score.
Now the t-score, if you look at this, the t-score, on my charts, it's like the third page. It's in the back of your book. If you look for the z-score on the back of the book, the z-score is the page right in front of it. It's also the tables in the back. It's also in that little handout in the middle, right there. Flip the page over one time on the back cover, and you'll find the t-score. All right. So at this point, I want to talk to you about the t-score and what the t-score means. Okay. So the first thing you have to recognize is on the left-hand side, this side right here, it says degrees of freedom. For this class and for this class only, the degrees of freedom will always be n-1. So at this point, I need to appoint somebody to be a degrees of freedom expert. For that, this person has a very big job. You are the expert for the class. If anybody ever asks you, you have to always know the answer. And I think it would only be appropriate that we go to somebody who is really, really, really conscientious about their work. Sorry, PJ, that eliminates you. It's Minerva. I think Minerva would be the person that we need to go to. Minerva, would you agree to serve as the degrees of freedom expert? You see, Minerva's kind of like Sarah Palin. She doesn't know what it entails, but she'll do it. Okay, I'm sorry. That was wrong. That was wrong on so many levels. Minerva, anytime I call on you and I say, what's the degrees of freedom? You have to say n-1. Did you hear that on the video somewhere? Okay, you're just that smart. Okay, so anytime I say, Minerva, the degrees of freedom is, you say? n-1. Very good. For the whole class, it's n-1. Now, next semester, you may take another statistics course. You may do something else. I'm sorry, PJ. I was just thinking outside the box that you might want to take another one. PJ said no chance. Now, area in one tail, this is all we're ever going to deal with. Don't worry about the area in two tails. Just don't worry about that. We're going to stick to the area in one tail. It'll probably make your life a little bit easier.
Right now or throughout the whole class?
Throughout the whole class. Okay, I don't think I told your friend that, and that might have messed him up.
Yeah.
Okay, so just put a big X through the area in two tails. Don't deal with that. Okay. Now, what is degrees of freedom, Minerva? Now, how many did we have last time? How many did we have last time? How many data points did we have? We had 8, right? We had 8. So degrees of freedom in this case will be 7. Minerva, did you know that? Well, if you had 8, n-1, and by the way, if you use your calculator for that, you fail. Just so you know, there's a second criteria for how do you fail the class. If I say 8 minus 1, you go, hold on. As one student told me one time, Dreyer, you can never be too sure.
7. 7. It's 7. Are you sure? That's a good point. Might want to try it again. Yeah, it's 7. Yeah, we don't deal with that. So, let's ask this question. We're constructing the what? A 90% confidence interval. So 90 is in the middle. Bless you. How much is on each end? 0.05, right? So we're going to go to our chart. Now remember, we're not looking at Now remember, when I go to my chart, this area is 0.05. That, remember what I told you, we're not going to look at what? We're not looking at the area in two-tail, so we're not even dealing with this. Right? Okay? So we're looking for 0.05. We're looking for 0.05 and 7. Does everybody see that? So the value we need is 1.895. So this is 1.895. This is negative 1.895. Does everybody see that? Okay. All right. So once you have that, just to refinalize, part A would be 0.90. This is 1.895, negative 1.895. Part B, you got to know the formula. The formula is x bar minus e is less than mu, which is less than x bar plus e, where e is equal to t times s over the square root of n. Now, you're probably going to look at that formula and look at it and think, that looks an awful lot like the other one we did. Remember the other one we did? Yeah. This one, x bar minus e is less than mu, which is less than x bar plus e. E is z times sigma over the square root of n. Okay, and this one is t times s over the square root of n. It really, they're identical formulas, which is why they're in the same section in the book. It makes sense for them to be in the same section because they're identical formulas. The difference is one uses a t-score chart and one uses s. Okay. Part C. What was our average? Can somebody remind me? So 66.25 minus 1.895 times, what was S? Not everybody speak out at once, please. You're confusing me. What was S? 18.54. Can we agree on that? 18.54. We get it off the sheet right here. This is S. Calculator told us what it was. We didn't know sigma. Okay, we didn't know sigma. All right. So we know S is 18.54. Divided by the square root of 8 is less than mu, which is less than 66.25 plus 1.895 times 18.54 divided by the square root of 8. Let's type this in and we'll see what we get. 66.25 minus 1.895 times 18.54 divided by square root of 8. How do I bring that back up to change the minus sign to a plus? Now in TI-83 you don't. And that little fancy one you got, that's what you do. Second, enter. Change the minus sign to a plus sign. You know, the interesting thing, Taylor, is I have students who, after they see that, they're like, "That's the best thing you said all semester." Like, of all the great things I talk about, that's the best one? Yeah, pretty much. Forget law of large numbers or central limit theorem or anything monumental. Second, enter. Okay, so let's write down the answer. We got 0.53. We got 53.83. And 78.67. I apologize. I should go 1 decimal point past 829. Right? We should go 1 decimal point past this one. 829. If this is 2 decimal points, this should be 3. Okay. How do I interpret? If we continue to take samples of size 8, we expect, what are we on, 90% of the sample means to be between 53.829 and 78.671. The E for this one is different than the E that you've seen before. Population is normally distributed, and sigma is unknown. By the way, this spells unknown. Okay. I thought you'd like that. Population is normally distributed, and sigma is unknown. Okay. All right. With that being said,